Good afternoon. It's 3 minutes past 1 o'clock. Again, I'm asking you if you can listen me and see the presentation on my screen.
Yes, good morning. No, good afternoon, okay. Sorry.
Yeah, we're in the middle. Okay, so this is lecture number 17. In principle, we should have a long lecture, as always, 3 hours, but I've put a question mark simply because today we don't have presentations from you, and the subject is only one, is the subject on adhesives, which it's fantastic, is amazing, but sometimes it's also a little bit heavy. So let's see, we will go on and decide if we are tired, and eventually we can stop before the time already scheduled. In any case, we don't have any problem about the program and about the time. Everything is under control, so no problems. Also, if we finish something before to what is already scheduled. Okay, what else? This is the material, nothing new for the slides, and yes, I've made some arrangements for the video. There is a new one, of course, and some of the previous videos I've placed in the YouTube folder, so you can simply find it just connecting on the links in the first file of this folder. What else? Next lectures, there are 4 lectures, so 2 weeks until the end of the course. And let me show the final program for your presentations. Is this one. So we have already listened Yannis, Clara, and Rainer presentations. For today, as I said, there are no presentations from you. Next Wednesday, there will be 2. So please check if everything is all right, or if I made some mistakes. Next Friday there will be 4, and so other 4s for the following weeks, for the last week, 4 on Wednesday and 4 on the last Friday. So this is the final and complete program. Please check it also on the folder on Dropbox. If there is something to change, please inform me about any problem you may have. Okay, so if everything is all right also here, we can close it. And going back to so this is the usual slides with the dates for the second part of the exam and for the official sessions. I don't want to repeat what we have said many times about the options you have. And what else? Okay, as I already said, today we need to go on with adhesives. That, as I mentioned before, is on my opinion, a very interesting subject. Before we go on, I would like to sorry, just a moment. Presentation. Not this. Just a moment. Okay. I will just to remember some of the main subjects we have considered during the last lecture. The story of adhesion and cohesion. I hope it's clear now. The attraction forces inside the same material, cohesion, and the forces acting between two materials. These are called adhesion forces. We have discussed about the advantages and disadvantages of adhesives compared to other joining systems. One of the disadvantages is the time, because we know that we have to apply the liquid adhesive. Then we have a certain time to combine the first element with the second, and then we have to wait for the hardening or the setting of the adhesive, and so after this time we can manage the joint, not before, because in this phase the adhesive was in the middle between a liquid and a solid, so it's only after a certain time that we can consider as completely solid, and so it's the time after which all the adhesive and cohesive forces are properly acting. So we need so we have two times to consider. The first is the time we have from the application to the coupling of the two elements. This is called open time normally, and then the other time is the time we have to wait for the adhesive to become solid, and this is normally called setting time. So time is we considered it as a disadvantages of adhesives, because on the contrary, if you use screws, for example, the joint is immediate. You don't have to wait for any change of state of the materials used, as in this case. And these two times are also strongly dependent, for example, on different factors. The environmental conditions, the moisture content, for example, of these two elements, the relative humidity of the air, and other factors related with the conditions in which the process was carried out. So last time we have considered the different theories. This is the mechanical theories. If you remember, we said that the adhesive penetrate inside the porosity of the substrates. Then it became solid, and so this prevent the two elements to be divided. So this is the principle of the mechanical theory. When we mention the chemical absorption theory, the formation of primary covalent bonds. So the theory is related with the chemical reaction of the two materials when they are bonded together. The diffusion theory, when the two polymers, the polymers forming the adhesive and the polymer forming the substrate are able to mix together, forming this interdiffusion of the molecular chains, so creating a junction, creating a union of the two materials. The electrostatic theory, we said it's something it's good to know, but we don't have real examples in our sector where this theory can apply. The absorption theory, we said, is the most important. Is related with the properties. The property of all materials to where the molecules generate some attraction forces, and we said that the absorption theory is strongly linked with the contact between the two materials. In this case, for example, we see that the number of contacts is very limited. This is, of course, at a microscopic level. So the final force, the final adhesion force, would be very, very limited. If we are able to improve the number of contacts, the number of attraction forces increases, and so from many weak forces we can derive a big adhesion force as the sum of all these little forces. In some cases, some previous lecture, some students ask me what is the difference between adsorption and absorption. Adsorption is something related with the surface. Absorption is something related with the bulk. This is better explained in terms of science. So you see the absorption here on the left is something related with the surface. Absorption is something related with the inside of one material. We also shown how the gecko and how the Spider-Man are able to walk on vertical walls. We said that the secret, the little secret, is is inside their fingers with this incredible number of little fibers, which create, as we said before, a large number of contacts. And again, many weak forces are created, but the final result is a big force. The gecko and Spider-Man are so able to walk on vertical glasses, for example. We said adhesion means contact. This is the experiment I suggested to you. So what happened when you touch a very cold surface? Some water here is initially melted, and so it's able to completely wet your finger, so creating a large number of contacts. Then the this little layer of water will cool down, so becoming solid again. And this is exactly the function of an adhesive. So finally, after some minutes, you are not able to detach your finger from the ice because of the creation of this large number of attractive forces between your fingers and the ice and the water, which is now solid. We try to explain the surface tension. We said that in a liquid substance, all these attraction forces are able to arrange in order to minimize the evidence, the attraction, and especially on the outer layer, there is an excess of forces creating a sort of a film on the surface. And the surface tension, we said, is the force required to break such forces. Here we have some examples of the effects of the surface tension, some drops of water, drops of quicksilver. This spider, which is able to walk on water because of the presence of this, we said, film created by these external forces. There are also some animals, so which are able to walk on water because of the presence of such film formed by the water molecules. And this is an experiment you can also do. Still, this can float on water because of again of the presence of this little film on the surface. Surface tension is for liquid. Surface energy is for solids. We said that in the case of solids, the molecules are not able to arrange to move themselves. And so there is always an excess of energy toward the surface. It can be considered a sort of attraction force against the molecules of other substances which are eventually placed close to the surface of this element. And so, who wins is surface energy or surface tension, which is higher, and the result could be different. In this case, the surface tension prevail on the surface energy. In that case, the surface energy is higher than the surface tension. I think quite simple. If we got the story of the attraction, mutual attraction of the molecule of a same substance. Again, it's another way to represent this story of surface energy and surface tension. Some examples of the surface energy of some materials. We have, for example, relatively high values for stainless steel, for copper, aluminium, and as we mentioned many times, we have very low values for plastic substances like for example, polyester 31, nylon 36. So it's normally very difficult to wet plastic surface because of their poor surface energy. I know it's on the other side. Sorry, ABS is 42, nylon 46. Where is PVC? PVA. I don't find PVC. PT is this? Maybe you know it. Polytetrafluoroethylene is maybe you know it as Teflon. Teflon is a material with a very, very low surface energy, which it's not always a disadvantage. Sorry, in some cases, like in this example, a low surface energy prevent the possible adhesion problems. For example, when you cook something. So in this case, the industry is looking for materials with a very low surface energy in order to prevent, in this case, the adhesion of food on the bottom of this cooking device. We spoke also about plasma, the fourth state of matter, this high energy state where we have radicals, free electrons, ions, and when the plasma touches a surface, the plasma produces some chemical change on the surface, and the overall effect is improving its surface energy. So especially for plastics, the plasma or the corona treatment, which is similar, are used to improve the surface energy in order to allow bonding or coating processes. It's very common in the plastic industry. That was all for the review of the last lecture. Then it's now time to go on. Okay, this was all the presentations we have already considered last time, with all the stories we have mentioned just now. I think we were here. We have now to quickly consider the general composition of the adhesives used in the furniture sector. In the preparation of adhesive, we have to consider that in the application phase, the adhesive must be a liquid, because we know now that wetting is fundamental. And so normally we need some solvents or water, or in order to make the adhesive liquid, or in some particular cases we can use also heat. Promote the melting of the adhesive. So there are some special adhesives we will see later on with the name of hot melts. This means that they are solid adhesives. They are sold as solids, and when they are used, they are heated at very high temperatures, so they melt, and so they are applied in this high temperature state to the substrate. Then the adhesive after the application must change its physical state from liquid to solid, And we have two possibilities. One is simply a physical process. So, for example, the evaporation of the solvent or the evaporation of water, or in the case of hot melts, the cooling of the adhesive. This is only physical. For other types of adhesive, we can also have the chemical hardening. So the resin molecules react together in order to form a more complex structure. We will see later on. From linear molecules, they will become a sort of network. And the chemical hardening will improve many of the properties of the adhesive. When the adhesive is finally in the solid state, it must develop the necessary adhesion and cohesion properties. We know why now. And according to the final use, also some special performance are required. For example, if the adhesive is used for external furniture, or if it's used for humid places like bathrooms or kitchens, it must develop some properties of specific resistance to such environments. The composition is very simple. We need the resin, which is the polymer which forms the adhesive film. It's the main ingredient. In some cases, we need some fillers. There are some minerals, silica or oxides or special salts, which act as fillers, for example, as real fillers. If you have a very porous surface, you need to fill these voids, and this minerals helps the adhesive to have these filling properties. Some additives, depending, as I said before, for example, for the final use, or in some other cases, they prevent the fillers, for example, to migrate toward the bottom of the can. There are different types of additives which improve some specific properties of the adhesives. And finally, as we said before, some liquid substances, water or organic solvents, to make the adhesive liquid for the application purposes. Consider the resin. We could have two types of resins. The thermoplastic. We have already introduced this term in the previous lectures. Thermoplastic means that the material became soft with temperature. When temperature increases, the adhesive tends to become soft. These are sorry. There are some problems in my screen. Okay. If we consider the polymer, the morphology of the polymer, thermoplastic resins are formed by linear polymers, like the chains you see here. should imagine these long chains, linear chains formed by thousands of atoms bonded together, as it is represented here. So, like you can imagine like a spaghetti dish. It's more easy, I think, for Italian students to imagine a spaghetti dish with all these chains mixed together, but without any real bond between them. So this adhesive based on the thermoplastic resins are one component adhesive. So you have only one can to use. They are generally very flexible and sensitive to heat and to solvents. So why they are sensitive to heat? Because if you start to heat a polymer formed by linear chains, they start to vibrate initially, then they start to move each other. And so this is the starting point for the softening and later on of the melting of the adhesive. The liquid state means that the molecules can move each other, so they are free to move. So again, I'd like just to quickly repeat then the adhesive is solid at room temperature, but when we heat it, we give some energy to these molecules. They start to as I said before, initially vibrate and increase the temperature. They start to partially move each other, and as we continue to hit the system, they finally are able to move one to the other. And so the typical behavior of a thermostatic resin is the initial softening and going on with heating. After a certain temperature, we can consider the polymer as a liquid polymer. This is the reason why they are sensitive to heat and why they are sensitive to solvents, because solvents can penetrate inside and they can divide the molecules and allow them again to move each other. So solvents can penetrate among the chains and let them to move each other. So this is why normally thermoplastic resins, thermoplastic polymers are soluble in organic solvents, because the solvents can interdiffuse inside and let the chains to move one from the other. And finally, thermoplastic resins are also sensitive to creep. Creep is the movement, is the reciprocal movement of the chains when they are subject to a constant load. If you apply a load, for example, in this direction toward the right, if the applied load is constant, you can slowly move the chains, some of the chains in this direction, and so the molecules can move each other, can flow each other. And this phenomenon is called creep. This is the reason why normally adhesive based on thermoplastic resins are tested with a specific test called the CRIT test, with a constant load applied, for example, for 1 month, and the result is not evaluated as immediate result, but is evaluated after, as I said, 21 days or after 1 month, because of this very, very slow but continuous movement of the resin one to the other. And this finally can determine the detachment of the two elements. These are the thermoplastic resins. On the other side, we have the thermosetting resins. In this case, the hardening or the setting of the resin is promoted by heat. So if you heat such resins, they become harder. Is exactly the opposite of what we have already seen for thermoplastic resins. And the reason is that during the hardening of such adhesives, as you see here, the different linear chains react each other, creating, as we said before, a 3D network. So finally, all the polymeric chains are bonded each other in one big polymeric structure. Normally, such adhesives, so the adhesive made with the thermosetting resin, normally they are two components adhesive. So there is an adhesive and the hardener, which are mixed together before the application. As we said, heat improves the cross-linking because heat accelerates the chemical reaction. Normally, the glue line is rigid, is stiff, and of course, the glue line is not sensible to heat, to solvents, and to water, as it is not sensitive to creep, because here for example, the solvent molecule cannot divide the molecular chains, so they cannot dissolve the adhesive. The same is for the creep. Here you can apply a load for how many days you want, but the load is not able to divide the resins, the resin molecules, and so for thermosetting resins, there is no reason to test their resistance to constant load, because from the theory, it's evident that the molecules cannot move each other after the chemical reaction. So normally, the thermosetting resins they have a better performance than thermoplastic resins, but as we will see, in some cases we prefer to use very, very flexible resins. For example, in the case of the production of armchairs, or in the case of the production of sofas. In that case, you need a very, very flexible adhesive to bond together, for example, the fabric and the foam. Otherwise, if you use a very rigid and stiff adhesive, when you sit on a sofa, the adhesive will break. So the thermoplastic, they have some advantages, especially the flexibility compared to thermosetting. For the rest, all the rest of the properties are surely better for thermosetting resins. The standard N223, EN 923 that we have already mentioned, divide the adhesive in 5 or 6 different classes. We will now quickly analyze all of them, saying something more for the types which are more important for the furniture sector. The glues are not so important for the furniture sector. They were in the past because glues, the class of glues include the adhesive base normally on animal or vegetable materials. So natural ingredients that were used a lot in the past, especially before the middle of the last century. What else to say? As I said just now, today they are completely substituted by synthetic adhesive, by resins produced by the chemical industry. We need to say something about the natural adhesives because today, because of all the stories we have already mentioned about sustainability and so on, today we can find on the market natural glues, especially for the production of wood-based panels, or adhesives made with natural ingredients. So they are the so-called bio-based glues or bio-based polymers, which are produced again by the chemical industry, but using natural ingredients. This is a new tendency, a green tendency, the green chemistry, which is using the ingredients coming from plants or seeds, in any case from the vegetable world, not from the oil like we are doing today. So this is the tendency for the future. Green products, green chemistry, sustainable industry, all these terms that we have already mentioned many times, especially in the case of wood, but also in the case of polymers, is today a goal for all the industries. What about the solvent-based adhesives? Just a few words about them. Normally, they are based on the different types of resins that are similar to rubber, dissolved in organic solvents. They are mainly known as contact adhesives and used especially in the upholstery sector. Maybe you know some of them, like the one I've shown here, the contact adhesive made by one famous company. They are used especially, as I said, in the upholstery. Upholstery means the production of sofas or armchairs, where these products find an exclusive use because of the flexibility. They are, as I've already said, based on thermoplastic resins, so are they sensitive to heat and solvents, sensitive to creeps, but the reason, as I've already mentioned, is that we need very flexible adhesives, because you can easily understand that when you sit here, the adhesive which is present between the materials must follow the stress caused by your weight, and so this is why this type of adhesive is predominant in this sector. For special applications, for example, in the case of the application of laminates, is also used because it's very simple. Also, the cost is very cheap. The setting is very fast, and so for little lots, it's sometimes a good option. For the production, for example, of furniture for a single shop. The companies they do not use extremely sophisticated equipment for the application and the drying of the adhesives. They can use such very simple products which are very fast in the setting, and which performance normally are quite good. Dispersion adhesives. This is, I think, the most important part related with the analysis of the different types of adhesives used in the furniture sector. Maybe you know them. Sometimes these adhesives are also known as a white glue because of the color of the adhesive. What is important here is to understand what is a dispersion. A dispersion is a system where we have two phases. One is the dispersed phase, is the raising, and the other is the continuous phase, which is normally water. Now, what is important to know is that raising and water are not chemically related. It means that they are not, they don't mix together. It's like water and oil, for example. You know that you cannot mix water and oil. They tend to remain separated. It's the same in this case. So the raising is not friend of water, I could say. So they tend to spontaneously separate if we try to mix them together. So what is a dispersion? A dispersion is a stable system where the raising molecules are dispersed inside the water molecules, thanks to specific substances called surfactants. We could imagine the raising not open, but like you see here, the raising is compressed in one particle. It's completely closed inside the particle with this special molecules called surfactants acting on the surface. Surfactants are special substances which have two parts. One part is, I could say, friend of water. So is the part on the external part, and the second part of the surfactants is a friend of the raising. So it's inside the raising. So it is dissolved by the raising. So surfactants are a sort of bridge between the raising particle and the water. So they have, as I said, two parts, two different parts. One inside the raising, one part is dissolved inside the raising, and the other part is dissolved inside water. So this is the way in which they are able to stabilize the raising particle in the water medium. Now we are going to see a short video explaining what surfactants are, and then we will we'll have a short break. You have an example of surfactants every time you wash your hands with a soap. So the soap is made by surfactants. And so if your hands, for example, are dirt because of the presence of an oil, when you use the soap, one part of the soap molecule is able to be dissolved by the oil you have on your hands. Then you put your hands under the water, and the second part of the surfactant of the soap is dissolved by water. So this is why you are able to wash your hands with the use of soap, because the soap, as I said before, acts as a sort of bridge between the substances which are present on your hands, like oils, paraffins, and so on. And they create a bridge with water. So when water flows, it's able to remove the oils from your hands. So there are also other examples of surfactants that now we will see on this video. I think it's better I close my headphones so you can listen better. Listen what. Moment.
It involves a solute dissolving in a solvent. But some substances simply do not want to associate with one another. As an example, when oil and water are added together, they form two distinct layers. This is because they are immiscible with one another. In other words, they do not mix. Even if you shake these two liquids vigorously, they will still remain immiscible. Let us look closely at what we have right now. There are tiny oil droplets interspersed throughout the water. We have just created an emulsion. What do you think will happen if we let this emulsion stand for 5 to 10 minutes? Let's pause the video and have a think. Press play once you are done. Since oil and water are immiscible, the oil droplets will reform the original layer. Common everyday emulsions include milk, mayonnaise, ice cream, and paint. These emulsions are mostly oil droplets in water. Emulsions can also exist as water droplets in oil. Real-life examples include margarine, lotions, and facial creams. The world's most popular emulsion is, without a doubt, ice cream. The main ingredients are milk or cream and sugar, along with flavoring and coloring components. So what prevents an emulsion, such as ice cream, from separating? Substances known as emulsifiers are added to stabilize emulsions. When making ice cream, egg yolk is commonly added. The active emulsifier in egg yolk is called lecithin. Too little lecithin will cause the ice cream to separate, and too much will ruin its texture and flavor. All emulsifiers have two components, a hydrophilic or water-loving head and a hydrophobic or water-fearing tail. If we added lecithin to our original oil and water emulsion, its hydrophilic head will prefer to associate with water and the hydrophobic tail with the oil droplets. This prevents separation and thus stabilizes the emulsion. In summary, an emulsion is a mixture of two substances that are miscible with one another. These emulsions can be stabilized by adding emulsifiers.
So again, I hope that this explanation was more clear than what I said. In any case, the main ingredients of every dispersions are in this case the polymers, water, and this surfactants or emulsifiers, as the video said. It's important also to consider that if the light ray is directed toward a dispersion, the ray is deviated by the water molecules, then is deviated by a different angle by the particles, resin particles, then it comes out and is deviated again by water and again. So finally, the light ray is not able to pass through a dispersion because of the discontinuity, the physical discontinuity. It's encountered during its trip. So finally, the light ray comes back to the observer. So all the emulsions normally are white. This glue, the vanilla adhesives are normally white simply because inside there is this discontinuity of water molecules and resin molecules. So as I try to explain, the light ray is not able to pass through the adhesive layer. Other examples are milk, again, milk is made with water, which is transparent, and oil, which is transparent, but the mixing determine the possibility for a light ray to pass through a glass of milk. Mayonnaise is white, ice cream is white. There are many examples of white dispersions. A white dispersion is a different dispersion, is also the fog. The fog is a dispersion of water particles inside air. And again, you know, the problems given by the whiteness of the fog, especially in winter. But okay, now we know that we have such adhesive which are produced in the form of dispersions. There are two types, vinyl adhesives and polyurethane adhesive, which are produced in this strange dispersion form. This is the last slide, and we'll have a break. Why it's so important to know this story of dispersions? It's important because the drying it's more complex than usual drying of the other adhesive. In this case, the resin particles must merge together during the transition from liquid to solid. If you remember what I have tried to show before, the resin particle is closed here, and in order to create a proper film, the resin must open and fuse, merge with the resins or molecules of the other particles. This must always happen, otherwise you don't get a proper film. So this process is called coalescence. It seems a strange term, but maybe you know other similar terms. Coalization. Coalization means a union. So what must happen here is that the different particles unify together in order to produce a proper film. So coalition means the union. Coalization is the union of different countries, for example. This process can happen only after a certain temperature. So below a certain temperature, this cannot happen. So these particles are not able to open and to merge with the other resin particles. And so this is really the last image I would like to show to you. This is a film of a dispersion adhesive which was applied on this steel plate with a gradient of temperature. Here we had -20. Here we had +20 degrees. And you see that in this part, the adhesive is completely white, and here the adhesive is transparent. So here the coalitions was good. In that part, the coalition was not right, didn't happen. So in this part, the hardening of the adhesive didn't form the film, but the single particles were not able to open and to merge with the other. So here we still have the resin particle closed, and not open and not fused with the other molecules. This temperature is fundamental because below this temperature, the adhesive does not produce a proper film. If you touch this part, it's like a powder. So it's not a film. You can really feel that the such particles didn't open and didn't merge with the others. This temperature, as I said, is fundamental. Normally, it's between 3 and 7 degrees Celsius. So it means that, for example, during winter, especially in the cold countries, if you apply an adhesive at a very low temperature, around 5 degrees, for example, the adhesive will not form a film, but will remain, the particles will remain divided. And after, for example, you produce chairs, tables, you combine together the legs with the structure. You don't see anything because the adhesive is inside the legs. But finally, when the product is exported, I don't know, in the United States, finally they will discover that the adhesion didn't take place. So you will have claims and maybe you will lost a lot of money simply because you did the process at a very low temperature, below the temperature at which the adhesive is able to merge, to produce this union of the particles. So sorry for this long speech about dispersions, but this is one of the main problems that the users of vinyl adhesive, one of the main problem they have, because they don't know this story of the minimum film forming temperature. It's not only a temperature suggested because of the speed of the process. It's something which really affects the formation of a proper film. And this is known as the minimum film forming temperature, and it is normally expressed in all technical data sheets of this type of adhesive. So when you will have on your hands dispersion adhesive, please read which is the MFFT value before you use it. Otherwise, you will get serious problems in your production. Okay, this is, I think, all for the moment. We can have a short or relatively short break. I think we can meet here at 30 past 2. So a longer break because of the subject that, as I said before, it's not difficult, but could be not simple and a little bit heavy not to understand, but to in Italian we say to digest, to put inside ourselves. Okay, so 30 past 2, we will go on again. Have a nice coffee.
Okay, Professor, have a nice coffee too.
Okay, thank you. Have a nice coffee.
Okay, here I am again, and so we can move on. Before going on with the presentation, I would like to show you this. This is a technical data sheet of a vinyl dispersion. You see here. I think can you see the technical data sheets of this vinyl raising? Yes, okay. And so you see is it's a polyvinyl acetate dispersion. So now we know what is a dispersion. With high solids content, okay, it means that there is a lot of raising compared to water, and particularly suitable for the adhesive formulation. Okay, and what I would like to consider is this minimum film forming temperature. It's 15 degrees. So now we know what is a dispersion, and we know that below such temperature, this product will not form any proper film, any proper adhesive film. So the resin particles will remain entangled, separated each other, and forming this white powder if dried at the temperature below the value indicated in such technical data sheet. So it's a fundamental, as I said, to understand what are dispersions and what the minimum film forming temperature means. Okay, so now we know how they are made. Vinyl adhesives are the most used in the furniture sector, and as is written here, their nature is thermoplastic. So we know that the resistance to heat, to water, and to organic solvents it's poor, and also the deformation under constant load can be also a problem. This is the typical behavior we said of all thermoplastic adhesives. There is the possibility to improve their properties with some modifications, in particular with the last one, the cross-linking of the raising by the addition of special polyisocyanate hardeners, which promote the cross-linking reaction we have already considered. And so there are on the market different types of vinyl adhesives, and they are classified with a letter D and the number 1, 2, 3, 4. And as the number increases, it means that also the resistance to water increases. So D4 is the best, for example, for the production of windows, for the production of garden furniture. D1 is the one used for interior furniture, for example, table, chairs, and so on. You could say that this is the worst. It's not the worst because, as we said before, this is the more flexible, and this is the less flexible. So it depends on what are your needs. If you need something which is highly resistant to outdoor climates, for example, D4 is the best choice. But remember that the final result will produce a more fragile, more stiff film than the use of the other adhesives. So there are suggestions depending on what you have to produce. There will be a different choice depending on the balance between the performance in terms of resistant to heat, water, and so on, and on the other side, with the flexibility that sometimes is fundamental for certain products. Okay, where are they used? As I said, they are number one in the wood and furniture sector for the assembling of chairs, tables, doors, cabinets, and so on. Application of laminates or impregnated papers, veneers, production of window frames, production of parquet. So there are many applications of such adhesive, and as I said before, they are one of the pillars of the furniture sector. In every company of our sector, you will find some vinyl adhesives for different applications. The other type of dispersions adhesives are the polyurethane ones, polyurethane dispersions. The story of dispersion is the same as we have already considered. In this case, the difference is represented by the raising. In the previous case, the resin was a polyvinyl acetate resin. In this case, it is a polyurethane resin. I don't want to enter inside the chemical details. Here is written that the polyurethane resin is the result of a polycondensation reaction between a polyisocyanate and polyol, but you can forget it. It's only important to remember is that in principle we have two types of dispersions in the furniture field. One is represented by polyvinyl acetate dispersions, and the other is represented by polyurethane dispersions. What are the advantages of such dispersions? There are three important properties. The first one is the so-called pseudoplasticity. It's better I show the meaning of this complex word. This is a diagram where we put we put the viscosity as a function of the shear rate, meaning the movement. There are some liquids like water, for example, which viscosity is the same in whatever condition you have water. It means if you mix water with low speeds or high speeds, nothing changes. The viscosity of water is always the same. But there are some other liquids which viscosity depends on the movements of their molecules. If the movements, for example, is is close to zero, so the molecules are standing. The viscosity is very high, as you see here. If you start to move, to mix the liquid, the viscosity becomes lower. And a typical example is represented by ketchup, that I think you know very well. When you buy a new bottle of ketchup and you try to put some drops of ketchup on your French fries, for example, you open the bottle, but nothing happened. The liquid remain inside the bottle. So what you do is to shake the bottle, and finally you are able to apply some ketchup on your French fries. So what happened with this ketchup bottle? You are exactly in this condition. So when you buy the ketchup, the liquid is still standing inside the bottle, so its viscosity is very high. When you shake the bottle, the molecules start to move, and the viscosity decreases. And so you are able to apply some ketchups on your French fries. So this is a typical pseudoplastic behavior. So there are many liquids presenting this strange behavior, but it's not strange. It's simply due to the composition of certain liquids. And what is the benefit, for example, for the adhesives used in the furniture sector? It's an important property because when we apply it, we apply it, for example, with spraying system. The molecules move very, very quickly, and the viscosity is very low. So a low viscosity is good for application purposes. But when they reach the substrate, the movement doesn't exist anymore, and so the viscosity raises up to very high values. And so this prevents the adhesive to be completely absorbed by the substrate. So this property, which seems strange, is a very good property for certain adhesives like the polyurethanes, because we need to apply them by spraying, and spray application needs very, very low viscosities. And so when we apply, the viscosity is very low. But when the adhesive reach the substrate, the viscosity immediately go up to very high values, and this prevents, as I said before, the anomalous absorption of the adhesive by the wooden substrate. So this is the interesting properties conferred by pseudoplasticity. So good spray application, because as I said, when the adhesive is in movement, the viscosity becomes very, very low. And when the adhesive reach the substrate, the increasing in viscosity prevent the absorption, the uptake of the adhesive by the substrate. So spontaneous increase in viscosity under static conditions. So this property is fundamental for certain applications. the compatibility with the, various materials is very good. Can be easily reactivated by heating, so it is applied. Then with some infrared lamps is reactivated, so is made fluid, and then it is ready for the bonding process. This is a typical pseudoplastic behavior, and there is here one example, the ketchup. This is a silly video presenting two guys which are able to walk on this liquid, as you see here, simply because it's a liquid with this pseudoplastic behavior. Okay, so you see that the difference when depending on the movement of the liquid, the viscosity is higher or lower. Quicksand also are an example of pseudoplastic liquid. So if you move, the quicksand becomes more liquid, and so the time you will have will be reduced. So the suggestion is to not to move if you get in trouble with quicksand. Again, this property is fundamental for coating applications, especially like in this case for ceilings or for vertical applications. Again, it's good to have a low viscosity during the application. So when the coating, in this case, is moved, so the application is easy, is faster. But when the coating is applied, it's good that the viscosity increases in order to prevent the falling down of drops. So also in the case of coatings, there are some special additives added to the liquid coatings to produce this pseudoplastic behavior. So you can easily apply the coating also by spraying, for example, on vertical elements. And when the coating arrives to the element, the viscosity increases, and this prevents the formation of droplets and the possible formation of drops on the objects you have already coated. The typical use of the polyurethane adhesives is the application of polymer foils on kitchen cabinet doors, as you see in this picture. if you remember, we have seen the process which is done by membrane press. So in one step, it's possible to cover 5 sides of the doors with polymeric foils, and for this special application, we need the use of such polyurethane adhesive, which can be sprayed on the surface of the panel, again in one step, and again, I don't want to repeat myself, but this story of pseudoplasticity is fundamental in order to prevent the adhesives to penetrate completely inside the MDF panel. Hot melt adhesives. I have already presented these special types of adhesives, which are sold as solid granules. They are completely free from liquids, from solvents or water, and as written here, they are applied at very high temperatures, normally ranging from 140 up to 220 degrees Celsius. The setting or hardening is very fast because depends on the cooling. So normally the cooling is very fast, and after some seconds you get the bonding ready. There are 4 types of this hot melt adhesives, the so-called EVA, ethylene vinyl acetate, the polyolefins, EPAO. We can forget the polyamides because they are not used today. And the last one is the class of polyurethane adhesive, hot melt polyurethanes, as written in here. They are used a lot, especially in the edge bending processes. We have already considered the edge bending processes, and in the majority of the cases, hot melt adhesives are used, and also in the case of profile wrapping, so the covering of this long and shaped elements, the main adhesives are again these hot melts. The EVA are the most used, and the reason is as always related with the cost. They are relatively cheap, and normally they confer, we can say, good properties to the final joint. They are thermoplastics, so here I have represented again what happened during their use. They are linear polymers that when are heated, they start to move each other until they are completely free to flow. So this is the melting state. Here the adhesive is liquid. Then in this state is applied, and simply by cooling it comes again to the solid state, where the molecules are more or less standing together. So this is why, again, as we know, the thermoplastic polymers are continuously sensitive to heating, to solvents, and so on. So these are good adhesives, as I said, with the normally good properties. But for example, you can imagine that they are not particularly suitable for kitchens, for bathrooms. So where, for example, you may have edges placed close to a dishwasher or close to an oven. So in that case, because they are sensitive to heating, they can become soft, and so the bonding can be affected by the heating devices like the ones I've mentioned before. So application, it's normally carried out at around 200 degrees because they are thermoplastic, they are sensitive to heat, sensitive to solvents, and the good is that they are resistant to cold. It's not so important because normally in our houses and in indoor environments, the temperature normally are higher than 15 degrees, so they are not so severe in terms of cold. The polyolefins, they are very similar to the EVA. What they have improved is the resistance to heat and solvent, which is a little bit better. In any case, they are thermoplastic, but as written here, the resistance to heat and solvent is improved compared to EVA. The third type of adhesive is the polyurethane adhesives. They are known with different names: isocyanate adhesive, polyurethane, HMPU, hot melt polyurethane, or hot melt moisture curing. So there are different names. We can also forget all these names and consider also only the most common, which is polyurethane hot melts. As written here, they are the most modern generation of hot melt adhesives, and what is different from all the rest of hot melts is that during their setting, during their hardening, there is only a chemical reaction involved. So this is the representation of what happened during the application. Again, we start with linear polymers. So in principle, the initial behavior is that of a typical thermoplastic polymer. But you see that there are some circles here, little circles, which want to represent some reactive groups. So they are melted by heating them. And again, because of the cooling, they became again solids. But at this point, a chemical reaction starts promoted by water, which is always present inside the materials which are bonded, or in the air of the environment, as we know. So the story doesn't go back to the initial state as we have seen before, but after this physical state, there is also a chemical step, which, as we see here, determines the cross-linking, so the formation of this network, polymeric network, which is now it's now a thermosetting polymer. So we start with the thermoplastic, but we finish with the thermosetting. So in this state, the adhesive is highly resistant to water, highly resistant to heat, and highly resistant to solvents and water. So this type of adhesive is the best solution, especially for environments where we have high humidity, or where we have heat sources like ovens, dishwasher, or in any case, whatever heating system used, for example, inside our houses. So the polyurethane or isocyanate hot melts, they differ from the others because the hardening is both physical and chemical. It's important to know this because the products are sensitive to moisture, so they must be supplied in properly sealed packaging. Otherwise, if the adhesive is exposed to air, it can absorb water, and so you will get this reaction inside your packaging, or inside your bonding line. So this is why the adhesive must be sealed in special packaging, which avoid the contact of the adhesive with moisture. And also the application must be carried out with special systems to avoid any contact with moisture. Normally, such systems they are also supplied with, for example, with nitrogen, in order to prevent air to come in contact with the adhesive. You know that air contain some waters, always some water, and this could be a serious problem for such adhesive. So special packaging system and special application systems must be used. They are suitable for bonding different materials, and again, the benefits I think I've already mentioned, that the good resistant to high temperatures and good resistant to moisture and solvents are the most important benefits of such solvents. Coming back here. So the initial process, we said, is similar to what we have already observed for the thermoplastic adhesives. This chemical process takes place only at the end, and the duration it's normally from, I could say,
3 days to 1 week or more. So this process, this chemical process, could be relatively slow. So the final performance is achieved only after some days, or as I said, after 1 or 2 weeks. So it's important to know this. So do not use immediately the bondings made with such adhesive, because initially they are resistant against such physical or agents or substances. Is it's not very good. So it's better to wait some days or even some weeks before putting in service the products made with such adhesive, because the chemical reaction can be particularly slow in some cases. The last point is the cost. It's clear that as the chemistry is more complex, formulation is more complex, also the use is more complex, as we have seen. They are more expensive than the other type of hot melt adhesive. So normally the furniture industry uses EVA adhesive for the majority of, for example, of edges, edging processes, and using the polyurethane only for special applications, as I said, for kitchens or bathrooms. So today, this is the situation in the furniture field. EVA for the majority of the products, and polyurethane for some specific application where we need a high resistance to water and to heat. Okay, the use, I've already said something about it. I think we can say something about reaction adhesive, and then I think we can close for today. And we can let the last part for the next lecture, but it's not so important. What I would like to do is to finish this part related with the different types of adhesive, and then next time we can repeat something and finish with the characterization. So it's good like this, I think. The reaction adhesives is the official name given by the EN 923 standard. I don't particularly like this name. I would prefer the name thermosetting, because reaction adhesive means that there is a chemical reaction involved during the hardening of such adhesives. So I prefer the name thermosetting or thermosets. In this case, the hardening or setting process is double. There is a physical process, as we said before, consisting the release of the solvents or the release of water in which they are dissolved or dispersed, and together with the physical process, there is also a chemical process which, as we already known, involve the chemical reaction, the cross-linking reaction of the resin molecule, creating this
three-dimensional structure, which is hard, infusible, and insoluble. Okay, I let something for the conclusion. There are different types of adhesives belonging to this class of reaction adhesives. Some of them we already know, in particular the first one, urea-formaldehyde adhesives, melamine formaldehyde, and phenol formaldehyde. Then we could mention also the silicones, the epoxy adhesive, and the isocyanate. I put them in gray because they are part of the furniture sector, but their use is very limited. So I don't want to consider them in our course. It's good to know that they belong to this family, but I don't want to add other subjects to this presentation. So urea-formaldehyde, we already know that the production is based on urea and formaldehyde. The combination of these two molecules produce what is known as a pre-polymer, so a little polymer, we can say. The reaction is interrupted, and with this pre-polymer, the chemical industry prepare the adhesive. Then, when the adhesive is used, the chemical reaction, the initial chemical reaction is completed by the use of an acid catalyst. So we can say that the adhesive the furniture manufacturer uses is something in the middle from the two raw materials, urea-formaldehyde, and the final polymer. So as I wrote here, the chemical reaction is interrupted, and it is completed when the adhesive is applied to the substrate. Very quickly, we know already a lot about such adhesives. The cost is very, very low. They're easy to use, good mechanical strength, not sensitive to grip, of course. They are not sensitive to organic solvents. They are completely transparent. And the bad news is that, as we already know, they are sensitive to hydrolysis. So we know that water is able to break some bonds of this resin. And the bad news is also that the byproduct is formaldehyde. So the fact that they are sensitive to hydrolysis determines two important consequences. The first is that they are not suitable for wet environment. In particular, you cannot use outdoors. And the second consequence is that of formaldehyde emission, something that we know very well. Urea-formaldehyde resins, they are mainly used in the preparation of wood-based panels. This is something we know from the lectures dedicated to wood-based panels. So we can say that in the furniture sector, Considering the adhesives, the three main pillars are this UR-formaldehyde adhesives, because they are present in the majority of wood-based panels. Then we said the polyvinyl acetate dispersions. They are the second pillar, because they are used in many different applications for the production of assembling of chairs, tables, doors, windows, floorings. So PVA dispersions are, as I said, the second pillar, and the third one is represented by the EVA hot melts, which are mainly used in the edge banding. So the three main adhesives, types of adhesive are UR-formaldehyde, PVA dispersions, and EVA hot melts. Okay, this is more or less all for UR-formaldehyde adhesives. Where are they used? Production of wood-based panels, the main application, the application of veneers, and okay, this is not exactly the role of the adhesive, but in any case, UR-formaldehyde resins, we know they are used for the impregnation of papers or the production of laminates. I didn't mention the other two types of adhesives, the melamine formaldehyde and phenol formaldehyde. In principle, they are similar to UR-formaldehyde adhesive. We already know that melamine formaldehyde are better in terms of resistance to hydrolysis. And the same is for phenol formaldehyde resins. The problem in both cases is the cost, which is considerably higher than that of UR-formaldehyde adhesive. So the problems we mentioned many times are really important, but as we said many times, the cost is always maybe the first parameter considered by the industry. So it's hard to move to another product if the cost is higher. And this is a typical example. Characterization. Okay, we can finish with this. There are different types of characterizations for the liquid adhesives. We can measure the density. We can measure the content of solids, the pH, the presence of free formaldehyde. I don't want you to remember all these parameters. I think it's important to know, for example, that the solid content is what remains when the solvents or water are evaporated. So it's in principle the resin, the adhesive, and the fillers. So if you compare two similar adhesives, of course, is important to know what is the solid content. So what you really use, because the rest, solvents and water, they evaporate, and so you buy something that you not really use. So they are important for the application, but then they go into the air, and so you don't. They are not part of what remains as the adhesive film. So very frequently a comparison between two similar adhesives starts from the solid content, so which is the best because contains more precious matter. The fillers are also important because the fillers, we said, are very, very poor materials like silica or metal oxides. So their role is important, but their cost is very limited. So sometimes it's also important to know how much is the content of fillers, because in principle they considerably reduce the cost of an adhesive. So again, a comparison between two adhesives could consider the presence of fillers because, as I said, the fillers are very, very simple and low cost materials, so they can significantly reduce the cost of an adhesive. The density is fundamental. This is something I always try to explain to the users, because adhesives are bought by weight. So, for example, you can buy a can containing 15 kilograms of adhesive, but you apply the adhesive by volume. The amount of the adhesive you need depends on the volume you apply. So the density is fundamental. So this is an example. It's a real example. These are two adhesives for the application of wood floorings. The density of the first one was 1.2 kilograms per liter, I can say. So this means that a can of 15 kilograms contains 12.5 liters. And a second adhesive from a competitor, again 15 kilograms, so the weight was the same, but the density was higher. It was 1.5 kilograms per cubic decimeter. And if you make the calculation, this means that this can contain 10 liters. So 2.5 liters less than the first one. So when you apply, again, you apply by volume. So this means that with this adhesive, you will glue a less reduced number of products than with this. So density is a little number, but can tells you a lot about the yield of the product you buy. So this is the reason why I normally try to explain these parameters especially to the users, because it's fundamental for what they buy, for what they spend for these materials. The body performance, I would like just to show to you some methods. I don't want you to remember that are used to test the adhesive, the adhesion strength according to an ISO standard, with some values suggested for vinyl adhesives. This is the creep test for vinyl adhesives, and there is a mass applied on the samples like this. There are 30 samples. No, sorry, there are 10 samples with a mass of 30 kilograms applied for 21 days. And so now I think you know why it's so important, this test for thermoplastic adhesives, because of the possible flowing of the resin molecules because they are not bonded together. They are simply close to each other, and so the load can produce their movements with possible failure of the adhesion. So the creep test is a fundamental test for vinyl adhesive, for thermoplastic adhesives. There is also a test for the resistance to high temperatures. Again, it's important for thermoplastic adhesives to verify if they can resist at 80 degrees under load. This is the classification we mentioned before, and the standard, European standard, tells you for which environment it's suitable, each class of vinyl adhesive, D1, D2, D3, or D4. And as I said, the D4 is the best for structures which are subject to exposure to water, condensation, and so on. So external structure in principle. There are some tests to verify the resistance to different climates, and okay, something related with the assembling system, just and the application systems, but okay, nothing I would like to describe. Also because some applications we have already seen in the other lectures. Okay, I think this all. I'm happy because I was able to finish this part of the program. Let me know if there is something to be clarified, if there is something I need to repeat. In any case, next Wednesday we will consider again the most important parts of the today lectures. Where we have analyzed the different types of adhesive used in the furniture sector. I think, as I said at the beginning, I think it's interesting to see how many different types of adhesives are used. They're different in their composition. They're different in the way they are used. It's interesting to see also their properties for different applications. Okay, that's more or less the word of the adhesive used in this sector. Any questions? Any clarification? No, it seems you are tired. Okay, so in any case, as always, I'm here for the following 10 minutes, 15 minutes, and so if there are questions, you can also contact me again for the following 10, 15 minutes. Okay. I can so close the lecture. I would like to say goodbye. Have a nice weekend, and we can meet again here by this remote system next Wednesday. Okay.
Okay. Bye bye.
Bye bye.
Thank you and bye
Thank you very
bye.
much. Goodbye. Bye bye.
Thank you. Goodbye.
Thank you. Bye.
Thank you. Bye.
Thank you.